move on and look at the weather forecasts. We know that some extreme weather events are influenced by like hurricanes, for example. And we welcome Sarah Keeley from ECMWF. We will tell us how we can fine-tune our forecasts by using digital models, by coupling data from the oceans and from the atmosphere. For the French speakers, you'll need to use headsets.
So I'm Sarah Keeley. I lead the ocean modelling team at ECMWF, and we're responsible for taking ocean models and coupling them to the atmosphere. And I'm going to focus today really on the value that we have, really on the weather timescales for how we see the ocean improving our forecasts. And I want to take you through a couple of examples. So just to start and set the context, the European Centre is an intergovernmental organisation, and we're supported by 35 member states. And our mission is to really provide global forecasts on the medium, so beyond 3 days, out to the seasonal timescales. And what drives us in terms of model development is adding additional complexity so that we can improve the forecasts for our member states on those timescales and support them as they develop their models for more detailed regional forecasts across Europe. Not only that, since our inception, and we'll talk about this later, our focus has been on working together to exploit the global observing system to give us maximum benefit in terms of our predictions. And that's something that's been touched on, talking about the Argo program and others, and how that revolution in ocean observing systems is really helping us to enable us to make use of the ocean model for weather forecasting as well. So we're home to 2 models now operationally. There's the integrated forecast system, and I'm going to talk about that today. That's our physical model, and that's been developed over the last 50 years. And in terms of skill, we see a day per decade increase in forecast skill. So when we started 50 years ago, the skill of our 2-day forecast is now the skill of our 7-day forecast, so giving a week ahead. And then the new child of ours is the artificial intelligence forecast system. This is purely atmospheric at the moment, but it's providing forecasts with comparable skill using the AI. So this is now operational since February of this year as well. So focusing on coupled weather prediction and how we bring the ocean into play. There's some key things in terms of a weather prediction that we need to know the initial state of the system, how the atmosphere and the ocean is. And we've known for a long time that the ocean plays a key role. So back in the 1990s, we added the surface ocean wave model to our system because we knew it was important for slowing down the winds as it uses energy to create the wave field when the winds blow over the ocean surface. But since 2018, we've included the ocean model in all of our forecast systems. And I'm going to talk you through some examples of where we tested and where we've shown benefit and where we're continuing to see benefit for that. And that's come about because we have the resolution to represent the key processes that are important. Jan's just shown some beautiful animations of those eddies in the system. And when we first tried to implement the ocean model, not capturing those western boundary currents and the loops in the eddies degrades our system because storm formation cares about the sea surface temperatures and the gradients in that. And that was something that was emerging in the late 90s and understanding that. So we need to be able to initialize our models as well, and then try and capture these interactions. And we need the computing power to do that too. So just to give you a feel for how our model is composed, and we don't do this alone. The IFS is developed in-house, but when it comes to the ocean and the sea ice, we draw on the European Community Model. This is NEMO. This is the nucleus for European modeling of the ocean. They provide us with the ocean model and the sea ice model. And we have two flavors of that. One that's about to become operational is the new SI Cube. But we draw on that experience, and we make use of it, and then we couple it to our systems for what we need for our weather predictions. So this was something that has changed in recent decades. Again, this comes back to some of the earlier talks today about Argo. We need to determine the state of the Earth system when we're making weather predictions, and we're really good at observing the atmosphere. We have lots of static observations in regular places. We have synopsations, but when it comes to the ocean, we're reliant on ships and buoys and floats, and until the most recent decades, we did not have a large observing system. Satellites are really good for giving us global coverage, but they only show us the top of the very, very top of the ocean. And as I'm going to show you in some of the examples, it's what's below that top surface that's really key for improving our weather predictions. So why couple a dynamic ocean model when we're thinking about timescales of a few days? The perceived wisdom was that the system doesn't evolve very rapidly, so why bother using the computational resource for this? Well, we knew we needed it for seasonal timescales and subseasonal timescales. We know about El Niño phenomena. We know that that has a global reach. But we also know that the ocean is a source of heat and momentum and moisture, and that is important for the local scale weather, and it's also important for storm formation. And then if we get to the polar regions, the sea ice is modulating the exchange of fluxes between the atmosphere and ocean, particularly in the winter, when the underlying ocean is very warm compared to the overlying atmosphere. So as our computing resource has grown, forecasting systems can allow us to increase that complexity, but also enable us to try and shoot for increased skill at longer lead times by exploiting the fact that the ocean is a slower evolving component of our Earth system. And the coupled evolution of the upper ocean to the atmosphere is important for enhancing and impeding storm growth, and we're going to show that with some of the extreme events. But also, if you're living in a coastal region, the way that local sea surface temperatures evolve is how you experience some of the local air temperatures, and we need to capture those too for coastal cities. So I'm going to give you a few examples. This one is looking at the sea ice cover, and you've got a comparison on the left and the right of the northern and southern hemispheres. And all this is really doing is trying to look at how rapidly the sea ice cover changes. And when I arrived at ECMWF 14 years ago, we persisted the sea ice over the course of a 10-day forecast. These colors are showing you how rapidly the sea ice changes. So if you look at the winter and spring periods, the lines are very close together. It means the rate of change of sea ice is not so great, and maybe we're not so worried. But when you look at the spring and summer, the summer and autumn seasons, when the ice is melting or refreezing rapidly, this isn't the case. So in the northern hemisphere, in the spring and autumn, it can change by 10 or 15% over the course of a 10-day forecast. And it's even greater in the southern hemisphere. So we instigated using a dynamic sea ice model, and this is just showing you a 24-hour change a bit closer to home. This is in the Baltic Sea. And we were just showing the difference in the forecast between leaving the ice as it was or letting the ice evolve. And you can see on the left-hand side, there's been a growth on the western edge of the, close to Sweden, there's a growth in the sea ice, and the local air temperatures, which is shown on the plot on the right, have dropped between 2 to 5 degrees. So if you're living in that region, you're going to feel a difference in temperature there. So there's a local impact. I'm not sure if this animation is going to play. You can see, so this is taken from the CMEMS website. This is just the last month of SSTs. And you can see the broad scale features don't change very much. You might argue that there's not some big change. But if you look at the western boundary current, so up near the coast of America, you can see the eddies evolving and changing, and those gradients matter. When we don't get it right on our forecast, we can see a degradation in the medium range when we don't capture this process well. So it impacts the predictability for Europe if we don't have these things in place. And now moving to something that's a bit more high impact. This is some test cases we did when we were ready to implement this operationally. This is a tropical cyclone Haiyan. It passed over very warm seas. The left-hand plot is the uncoupled model, so we're not using a dynamic notion, and the one on the right is the coupled one. And you see not so much difference between the pair of them. You'll also note there's little round circles. This is showing where the floats are and where they're comparing to observation. So if the color matches in the circle with the surrounding background, then we've done a good job at predicting the SST. In this, we just keep the SST static, so we don't see any evolution. So then we had a storm Niguri. And when this was forming in the uncoupled model, you can see it's under very warm temperatures. The temperatures are above 30 degrees centigrade, and the SST is the fuel for that storm. So we had the potential that the storm was going to grow and intensify. But when we ran the coupled model, this didn't happen. And that's because of the structure of the temperatures of the ocean beneath. So what I'm showing here on the left is the subsurface ocean, the vertical profile, at a point where the storm crossed. And on the left-hand side is the one for Haiyan. And you see there's a very deep, warm region of, you can see the yellow temperatures in their 20s. Well, under Niguri, there was very warm temperatures, above 30, but very shallow. And as soon as the storm hits the region, the winds generate upper level mixing, and you mix the cooler waters in those purple colors up to the surface. And it retards the storm because it doesn't have the same temperatures to feed the storm growth. So we see a difference in intensity and also slightly different tracks as well between the two. And so with our coupled system, we're able to capture what's a cold wake that's left behind from the storm and increase the fidelity of that prediction. So I think this has just said exactly what we've talked through, but the vertical profile of the ocean matters in capturing the storms. And so that's why things like these Argo floats that are giving us profiles are so key for us being able to predict the system well. This was just a more recent example. This is showing an SST forecast again for the Baltic region. This was in the summer in 2023, and a storm passed over the region. There were warm seas, but the storm persisted over southern Sweden and Norway for several days. And this is the start of the forecast on the left, and then the change in the SST on the right. And we've seen large-scale cooling, so the difference between day 1 and day 2. And you can see that this is, again, really important for making sure that our short-term forecasts for those coastal regions are also well captured. So then I wanted to finish by looking towards the future. So on the left is our current operational resolution, and on the right is a prototype of higher ocean resolution and higher atmospheric resolution. So we're going from 9 kilometers down to 4. And you can see the progression of these two storms. And even though both are coupled, we see that we improve the representation and the evolution. Firstly, you see the increase in the atmospheric resolution. The storm deepens on this right-hand side because we have higher fidelity in the atmosphere. But we also see the interaction with a higher resolution ocean. And again, this cold wake that impedes the storm. And you'll see that by the time we reach the end, the storms have different characteristics between the two. And so this is the way we're continuing to assess our systems and improve the coupling, but also the resolution gives us something for the future. And then I just wanted to go to a final statement about whether the coupling matters. This picture is very ECMWF centric. It's one of our scorecards. It's a way of assessing and giving you a quick visualization of how the model is performing. We assess this every time we upgrade our forecast system. And so you're seeing various metrics. The bars in each column are different regions, and then each day of the forecast. So we're seeing 10 days. The thing that we always want is we want blue. It means higher correlation and lower error. We want a blue scorecard. And what we did was we reran our current operational system, and we took the ocean back out again to see what value the ocean was giving us. If it's blue on this, then we're improving our forecast system by having a dynamic ocean model underneath. And you can see that, I mean, this is very striking. When we have a model upgrade, it's usually far more neutral. This is a strong indication that running the ocean in our numerical weather prediction system is crucial for giving us skill. You see the really strong colors in our 2-meter temperatures, the really dark blues, but getting that surface ocean right improves the depth of the entire atmosphere. We know we still have problems in the southern hemisphere. Partly that's because it's less well observed. We don't have so much observations there. And also we know that we don't have the coupling at the moment between the waves, the surface ocean waves that can actually impact the evolution of the sea ice, and that's something we're working on at the moment. So hopefully I've convinced you that it's worth the computational power to include the ocean model as well as the atmosphere to the MWP. It's essential that we have good ocean initial conditions and the observing systems to do that. And the increased resolution is important for us to capture those fine-scale features that the atmosphere really cares about. And the coupled MWP works well and improves the atmospheric forecast skill. And many operational forecast centers around the globe are developing or using these coupled systems now. And I would say, finally, AI is playing an increasing role in our forecast systems. We're currently developing data-driven components of all of our marine components as well, the waves, the sea ice, and the ocean. And we're exploring what coupled systems and forecast systems mean in the future in the context of AI models as well. Thank you for your attention.
Merci, Sarah. Thank you, Sarah.